When there's imbalance between generation and demand, system frequency will change. Let me explain how frequency control is imposed and why frequency will change like this. When there's a drift of frequency, the first thing that will happen is inertial response of the rotating masses according to Newton's second law. If you write down the pre-disturbance kinetic energy equation, we'll find it is proportional to the square of frequency. And if we take derivative of kinetic energy, we'll find change in power is proportional to the derivative of delta F. That is to say, if there is a delta P and we do nothing about it, then there's always a d delta F dt, and this delta F goes to infinity. The primary response, or frequency containment, is to stop frequency drift. But there is a final value error in this control, so we need a mild integral control to eliminate this error. After all this, we need to release the control effort we used to be prepared for the next disturbance, and this is called tertiary regulation. We'll talk about the details later. Now I'll show you how these regulations are achieved by modeling generation, demand, and control mechanisms. This diagram covers everything I'm about to talk. But don't panic, you're not required to draw it. Just follow me, and by the end of the day, you'll be familiar with all the components and parameters in this diagram, and you'll be able to explain which part is what. Let's start from the torque. It's a bridge between P and omega. In steady state, the mechanical torque is equal to the electrical torque. When a disturbance happens, you can start from Newton's second law, multiplying it with omega 0, and take a Laplace transform to find the model of delta Pm, delta Pe, and delta omega. The load can be further decomposed as frequency-sensitive and insensitive parts. The frequency-sensitive parts include induction machines and damper windings of synchronous machines. If you see terms in this diagram whose denominator is a summation, then there is a merging of feedback control blocks like this. You can explore the details here, but it's not a big deal if you just take them as a whole. Usually we don't have direct control on turbine mechanical power, but instead we have direct control on valve position. So we add this relationship between the delta Pm block. Then how does the governor control the valve in an isolated generator? The idea is that if the rotating speed is higher than expected, then we turn our valve down a notch to let in less steam. We compare our omega with an omega reference and pass that difference to an actuator, including an augmentation block and an integral block. Notice that the speed governor tries to maintain the reference speed regardless of the electrical load. This is a problem because when the generator is paralleled into the grid, if there is a mismatch between omega grid and omega reference, the speed governor will attempt to change the system frequency to its reference. However, this is impossible because the system is infinite, and the result is that the turbine valve will either open to its maximum or close to its minimum once there's any mismatch of frequency. Therefore, we need droop control to make this more reasonable. The essence of droop control is that when there are several generators in parallel, generators with large ratings should change output more towards the same direction to deal with the frequency change together. Before adding droop control, the frequency and power is like this. The set points correspond to the reference frequency, and other than that, the power is either minimum or maximum. But after we use droop control, there's a droopy line here and we can control the slope of this line. For the same frequency change, we hope generators with higher rated power to have more delta P. You can think of this process as pouring waters in leak bottles, and the final result is that the water level is the same. Two factors influencing the increased water allocation is the diameter of the bottle, which is like ratings, and the initial position, which is like the load reference point. The load reference point can also be adjusted. So the valve position change delta P valve is multiplied by the droop constant R as a feedback of the path from rotating speed to delta P valve. We can add the load reference set point and close the loop. There are governor, prime mover, generator, and droop involved. You can finally get the control diagram from load disturbance delta PL to speed or frequency change. If we give a step change to the load, then by the final value theorem and Laplace transform, we can calculate steady-state speed error. The frequency containment is achieved, but the error is non-zero. It's proportional to the disturbance delta PL, and is also affected by the constants D and R. Bigger system damping D is desired. The bigger D is, the bigger load sensitivity is. That's reducing the reliance on generation response, and the frequency shift will be reduced. And bigger system inertia M is also favorable in inertia response to reduce the initial rate of change of delta omega. But both D and M can decrease due to power electronic devices in systems. Up to now, after these control efforts, the power generation and load mismatch is eliminated, but we still have two problems. One problem is there is a steady-state error on frequency, and the other problem would be that there's also a change in the timeline power flow between two interconnected regions compared with the pre-disturbance value. We can check this by DC power flow calculation, and the derivative of angle is frequency, and we can do a Laplace transform. This means in two synchronous areas, if there is a disturbance in only one area, then both areas will be involved in inertial response and primary frequency control. However, this is undesired. First, frequency errors correspond to time errors, and that would affect clocks with AC frequency as a base. We don't want disturbance in one area to influence clocks in other areas. Secondly, timeline flow errors lead to sub-economical operation. To solve this, we can use AGC, automatic generation control. First, the generation and demand mismatch should be solved within the area where it occurs. So we want to locate the original disturbances and eliminate the timeline flow error. We drive our AGC with area control error ACE by imposing a bias factor on delta omega for each area to estimate its true frequency response, and combining it with a timeline flow disturbance. Parameters involved here are D and R, which correspond to load composition and generation ratings respectively. Second, we want to eliminate the steady-state error, so we add a mild integral control block on delta omega to be added with the electric power reference. When there are multiple generators, the response is allocated among generators in inverse proportion of marginal cost, and participation factors are calculated by economic dispatch. ACE should be small and its average should be zero. Control errors should be small to avoid haunting of noise and issues with ramping limitations. A short summary for primary and secondary frequency control. Primary frequency control is imposed once turbine speed deviation is detected. No communication is required and economics is not considered. Secondary control or automatic generation control is triggered by a central signal and can bring frequency back to its set point value and bring timeline flows of connected systems to pre-disturbance values. Economics is considered here. Tertiary control can bring generators providing control efforts back to their original set points, and is done manually 20 to 30 minutes after disturbance. Thank you for watching, and I'll talk about economic dispatch in the next video.